Okay, now, welcome back. Now in this video, I'm going to now extend this to a general case and show how the integral test works for a general series. Okay, so we showed two specific series where it works, but now let's consider a general series. So let's consider a series that has positive terms. Okay, again, remember that's one of the conditions we need. And also, let's say there exists a function such that the function is continuous, positive, and decreasing, such that f of n, right, f of n equals a sub n. Right, for all positive integers n, right? So for all n greater than or equal to 1. Okay? So let's say that's true. Okay. Then there is going to be, for any integer k, the kth partial sum, s of k. Okay, so for example, if this is true, let's erase this. So for this side, oops. So for this side, for any positive value k, we're going to have this. We're going to have s of k, which is equal to the summation of n equals 1 to k. That's going to be less than the integral, right? So okay. And so again, if we add a sub 1, so that's, we're going to say, oh, sorry, hold on. Is going to be less than a sub 1. Okay. Plus the integral from 1 to k of what? F of x dx. Right? That's always going to be true. So, now what is also going to be true? What's also going to be true is that this is going to be less than what? 1 plus the integral from 1 to infinity. F of x dx, right? So now that's where the improper integral comes in. So therefore, if the improper integral converges, then the sequence of partial sums is bounded. Now, since this is an increasing sequence, why? Because remember, all of the terms are positive, right? So it's going to be an increasing sequence of partial sums. And so if this is convergent and we have an increasing sequence of partial sums, and again this is a continuous decreasing positive function of x, then we have a bounded increasing sequence of partial sums. Therefore, the sequence of partial sums by the monotone convergence theorem must converge. And then the conclusion is the series converges. Okay? So let me say that again. Therefore, it says, if this converges, right? And since the sequence of partial sums, since this converges, then that means that the sequence of partial sums is bounded. Okay? And since the sequence of partial sums is an increasing sequence, if it is also bounded, then again, by the monotone convergence theorem, it converges. Right? And then we can conclude that if this converges, then what? The sequence of partial sums converges, which means that the series converges. So basically, what it comes down to is if this converges, then the series converges. Okay? Okay, so now, on the other hand, what about the other side, right? So now what about on this side? Well, then on this side, what do we see? We see that for S of k, which equals the summation from n equals 1 to k of a sub n, well, this is going to be greater than what? It's going to be greater than what? The integral from 1 to k plus 1 of f of x dx. Okay, so now, what happens? If the limit, right? So if the limit as k approaches infinity of the integral from 1 to k plus 1 of f of x dx equals infinity, then the sequence of partial sums is unbounded, and therefore the series itself is unbounded. And the sequence is, well, let me just say it this way. If this equals infinity, then the sequence of partial sums is unbounded and therefore diverges. And if the sequence of partial sums diverges, then we know that the series diverges. Okay. Now, since f is a positive function, then if the improper integral from 1 to infinity of f of x dx diverges, right, then we know that the limit is going to equal infinity, right? So since this is positive, and if this is divergent, then we know the limit goes to positive infinity. So we can conclude that if, so it comes down right down to this, okay? So just like before, we can say now, if this diverges, right? Or in other words, I'm sorry, if, let's redo this, hold on. This. So basically we can conclude that if this diverges, then the series diverges. And that's it. So next we'll introduce the theorem for the integral test.